All right, well, let's just dive straight into this. Welcome to today's Explainer, where we're going to unpack a massive, literally newly published breakthrough in the world of nanotechnology. We're talking about a discovery so perfectly symmetric, yet honestly so structurally surprising that it is shaking up decades of established material science. Today, we're looking at the brand new 80-atom boron buckyball. It's this microscopic marvel that was just proven to exist, and the story of how scientists captured it, well, it involves lasers, electron racetracks, and a nearly 30-year quest to prove the gold standard computer model's absolutely wrong. Let's get right into the evidence.
So, to really understand why this is such a big deal, you have to look at the reigning heavyweight champ of the nanotech world, which is the legendary carbon Buckminster fullerene. Now, discovered over 40 years ago, this perfectly symmetric 60-atom molecule essentially kickstarted the whole nanotech revolution. But meet the new challenger on the block, the boron buckyball, made of 80 atoms. Boron is carbon's scrappy next-door neighbor on the periodic table, right? And for decades, researchers have been wondering, could it actually mimic carbon's incredible structures? Section 1. Carbon's famous shadow, the Goliath of nanotech. Before we can fully appreciate our underdog here, we need to understand exactly what it's up against, and it really all boils down to carbon's incredibly unique electron configuration. Because of the specific, highly versatile way its electrons are arranged, carbon atoms can effortlessly bond together to make just an astonishing variety of shapes. We're talking about the structural flexibility of nanotubes, the flat, 2D planar perfection of graphene, and of course that original 60-atom buckyball. These shapes have totally transformed energy technology, modern medicine, advanced manufacturing, you name it. Carbon has essentially cast this massive, intimidating shadow over every other element. Moving into our second section, boron's 30-year quest, stepping out of the shadow. This brings us to a really remarkable scientist over at Brown University, chemistry professor Lai-Shang Wang. And look, this discovery did not just happen overnight. Professor Wang has been on a singular, laser-focused mission for nearly 30 years to see if boron could finally step out of carbon's shadow. The thinking was, if boron could form similar structures, they might actually possess properties even more interesting than carbon's. So in 2013, his team successfully showed that clusters of 36 boron atoms formed a planar, one-atom thick disk. The very next year, in 2014, they proved that a 40-atom boron cluster could form a hollow cage, kind of similar to a buckyball, but lacking that perfect spherical symmetry. And that brings us to the ultimate 2026 milestone, the discovery of the perfectly symmetric 80-atom buckyball. But here is the crazy, dramatic irony of this entire timeline. Going into this experiment, Professor Wang himself stated, and I quote, "I really didn't think this structure was going to be stable and that we were going to disprove its existence." Just think about that for a second. The lead researcher, the guy who dedicated 3 decades of his professional life to this specific element, went into this experiment fully expecting to prove that the boron buckyball was biologically and chemically impossible. Section 3. The electron racetrack. How to weigh the invisible. So how exactly do you weigh and measure something you can't even see? Well, this is where the physics gets incredibly fun. To test these microscopic clusters, Brown graduate students Hyun-Wook Choi and Denise Kahraman used a technique called photoelectron spectroscopy. Think of it like a 4-step recipe. Step 1, they blast a solid boron target with a high-powered laser, basically knocking off a plume of boron atoms. Step 2, they cool this plume extremely rapidly so it forms nanoclusters of varying atom counts. Step 3, they weigh these clusters in a mass spectrometer to isolate the exact clusters that have exactly 80 atoms. And finally, step 4, they zap that specific 80-atom cluster with a second laser. This laser knocks an electron completely out of the structure and sends it flying down a long, specialized vacuum tube that Professor Wang affectionately calls his electron racetrack. The core mechanic of this test is just brilliantly clever. When that second laser knocks the electron down the racetrack, the precise speed at which that electron travels determines what's known as the binding energy spectrum. Basically, in plain English, it tells the researchers exactly how tightly the cluster was holding onto its electrons before it got zapped. That resulting spectrum acts as a direct, undeniable structural fingerprint for the cluster being tested. Put simply, the shape of the spectrum tells you the shape of the molecule. Which brings us to Section 4, a surprising spectral signal, the moment of truth. You have to imagine, tension was pretty high in the lab, mainly because of what the team had seen in the past. Older, larger boron clusters had been producing these really relatively featureless readouts. They just weren't visually interesting, which usually indicated the molecular structures weren't that interesting either. So when Wang actually left for a trip, leaving his students to test the 80-atom cluster, his exact expectation was failure. He noted, "My attitude at that time was that this was probably going to be a low symmetry thing. I thought, we'll get this ugly spectrum, publish it, then it's the end of the story for this B80 cluster."
But then, the plot twist. Wang returns from his trip, and his student shows him the data. And the spectrum wasn't ugly at all. In fact, the readouts had these massive, distinct, sharp peaks sticking out like sore thumbs. Now, in photoelectron spectroscopy, a simple spectrum with huge distinct peaks implies one very specific thing: a highly stable, highly symmetric structure. Working with colleagues around the globe, they confirmed it. The only molecular shape that could possibly produce this beautifully simple spectrum was a perfectly symmetric 80-atom buckyball.
Now, you might be wondering why this physical discovery was such a massive shocker to the scientific community. To understand the controversy here, we have to talk about the current gold standard computational method for determining molecular properties. It's called density functional theory, or DFT for short. This is the heavy-duty theoretical framework that supercomputers use to predict whether a molecule will be stable or whether it'll just instantly collapse in on itself.
And this created an absolute epic clash in material science. On one side, we have the brand new physical evidence, an undeniably symmetrical, highly stable 80-atom boron buckyball, verified in the real world by the electron racetrack. On the other side, we have the incredibly trusted DFT computer models. And those models explicitly stated that the boron buckyball should not be stable. It was supposed to be literally impossible. So the physical experiment and the world's best computer model were at total, complete odds.
Faced with this massive contradiction, Wang didn't back down. After doing these exhaustive searches of possible 80-atom configurations, all the physical signs still pointed straight to the buckyball. So he drew a really bold conclusion against the computational Goliath, stating, "I think the DFT calculations are wrong in this case. I think DFT has some of the bond lengths wrong for the B80 buckyball, and that leads to incorrect predictions for its stability." And guys, this is what makes science so thrilling, right? No matter how advanced our computer models get, nature still holds surprises, and hard physical experimental evidence can still rewrite the rulebook.
Section 5, the future of boron, moving out of the vacuum.
So now that this incredible discovery has been officially published in the journal Chemical Science, what happens next? Well, there are massive hurdles still ahead for our underdog element. First off, Wang's lab currently only creates these magnificent 80-atom clusters inside a high-tech vacuum. Obviously, we don't live in a vacuum. Second, they need to deeply investigate the chemical reactivity of the molecule. Boron might just be way too reactive to stay intact in normal, everyday air, which leads to the ultimate holy grail goal here: synthesizing the boron buckyball in bulk form outside of a vacuum so it can actually be used to build the next generation of real-world advanced materials, much like its carbon cousin.
But there is a tremendous amount of optimism in the air right now. Remember that one atom-thick, two-dimensional boron disk Wang discovered back in 2013? Well, it only took 2 years for other labs to figure out how to stitch those disks together and synthesize bulk boron in 2015. So Professor Wang is super hopeful that the scientific community will rally around this new buckyball with that exact same incredible speed. The precedent is there, and the race is officially on. Which leaves us with this final, provocative thought. We know the 80-atom boron buckyball is real. We know for a fact it completely defied the computer models. But will it actually survive ambient conditions to trigger the next massive leap in nanotechnology alongside carbon? Or will it just remain a fascinating but ultimately fragile laboratory novelty? I guess only time and a whole lot more science will tell.